scattering in, you up and rolling there? Okay, so Colin has given you bits and pieces of scattering in her introductory lecture and then her lecture yesterday. So today we're going to take a little bit more detailed look at scattering and then you'll know enough at least to run Hydra Light. So you've seen this a couple of times and it's on the wall over there, but you know the bottom line is I've got this kind of organizational chart of all of optical oceanography, at least that we're going to do it in here, and you guys have been up here looking at the absorption box and learning how to measure absorption and all of that, and we're now going today to look at all these boxes here that have to do with scattering. And you'll notice up at the top there's this thing called the volume scattering function, and if you know it, then everything below that is derivable, and if you know absorption, then that all ends up giving you everything you need to know about the optical properties of the medium, the absorption coefficient and the volume scattering function. And then those things are going to feed down to all these other things that we're interested in. And as Colin has said, these IOPs, they depend on things like the concentration of what's there, the size distribution, internal structure, and all of that, but they do not depend on the light field itself. They're inherent properties of the matter. And so that means you can take a water sample, take it in the laboratory, and measure IOPs. So that's what you've been doing a lot of. Okay, so today, once again, I'll review the little basics here, definitions and so forth, and seeing all this stuff about 5 times is necessary before it really begins to soak in on what's going on. We'll look at data for scattering by different kinds of particles, and eventually we'll end up with some models for scattering that you can then use in Hydra Light, for example, where you put in things like chlorophyll concentration or the concentration of mineral particles or bubbles or whatever, and then you can model what those things do to the light field. Okay, so just back up one more time, the definition of the volume scattering function, which often seems to be a little confusing to people, but it's no more complicated than absorption. But basically we've got a little volume of water here, so there's some thickness delta R and some little area A, so that gives us a little volume of A delta R, which is delta V here. We're going to put in radiant power onto the face. Let's just think of this as a little cuvette, and inside that there will be some scattering. Some of the light will go straight through, some will get absorbed, but some is going to be scattered out in various directions. And so we're going to assume that whatever's in here are randomly oriented particles, so you don't get more scattering in this direction than you do in some other direction. If this is the direction light's going, what's scattered by 40 degrees here is the same as what's scattered by 40 degrees here. Now that's not always true, but for the ocean it often is. And then we're just going to sum up the scattering that's through some angle, scattering angle psi I use, and then anywhere in this azimuthal ring that's out here at psi to psi plus d psi is what we're going to measure by our detector. And when you get to using the list next week, this is exactly what it's doing. It has these little ring detectors. Anyway, we assume that our thickness here is small enough so that there's only one scattering event per photon, if you wish. So it comes in, it either goes through, it gets absorbed, or it gets scattered once. And then the definition says, look, I know how much power I put in, I know how much is scattered, so there's some little amount delta phi scattered, and I'm going to normalize how much is scattered by what goes in, by the thickness of the little volume of water, and by the element of solid angle d omega. Then conceptually, if you're a mathematician, you think about letting delta R and delta omega go to 0, and you get this derivative thing. In the real world, of course, you have always finite size solid angles, finite path lengths, and so forth. Now, another way to write the same thing is this. We'll say a little bit more next week, but there's a quantity called the intensity. And intensity, if you remember, radiance L is power, so watts per square meter per steradian per nanometer if it's spectral quantity. And then there's irradiance E, which is watts per meter squared per nanometer. And you'll see next week, and Colin's already mentioned, you get this thing by integrating this guy over solid angle steradians. There's another thing, intensity, that is watts per steradian per nanometer. And that's used to describe light emitted by point sources where there is no meter squared, there's just a point source. And so you look at the power that's going out divided by how much is going into some little solid angle delta omega. So the intensity is how many watts are in there per steradian of solid angle per nanometer. And so here it is, intensity is power per solid angle. So with that definition of this thing, intensity, I can write the scattered power is the scattered intensity times the solid angle. Then irradiance is power per unit area. Volume is area of the face times the thickness here. And I can simply use these to rewrite this equation. And so if I multiply, say, phi over A is irradiance, and then multiply times A delta R is volume, and then power per steradian is intensity. So you can also write this and see it defined as the scattered intensity per unit volume, and that's why it's called the volume scattering function. So it's just another way of rewriting the same thing, and you now have an irradiance here instead of a power. But that's the definition, and that's sort of all you need to keep in mind. Now, these things, however, are often kind of hard to plot because now instead of having a single number like the absorption coefficient, you have a function of scattering angle. And in general, it may be the scattering angle relative to the distance or the incident direction, but also an azimuthal angle, which we're ignoring here. So now instead of just a number, you have to plot up some kind of function. Well, it usually is plotted like this. Here's the volume scattering function, and I've actually divided that by the scattering coefficient, so that's really what's called the phase function we'll get to in a minute. But you get some function that looks like this. So here's a log linear plot. Here's the same thing on a log plot. And for ocean particles, typical particles, you get very high scattering at very small angles and much less scattering at large angles. And there's usually a minimum at somewhere around 120 degrees, and then it may go back up just a little bit. So that's simply a plot of a typical ocean scattering function, that kind of behavior. And then I just took that and drew this kind of three-dimensional view of it, where if the light's going towards the North Pole, and then it scatters out in all directions. So there's really, really high scattering here, the little red dot at small angles, and then if you go out to a scattering angle from here to here, maybe 5 degrees or so, now you're getting the green here is the green here, and then the light blue and the light blue, and finally you get out to 90 degrees, which is the red line. That's kind of this purple color. And so it's just another way of viewing that really I have a three-dimensional thing here, which is this volume scattering function. But in this case, if I plot the scattering along this azimuthal angle or this one, they're all the same. Now, when you get to playing with polarization, that ain't true. You can have the polarized light here, and more will be scattered in one direction than azimuthal direction in the other. And Ken will get into a little bit of that next week. But right now, this is all you need to know. This is kind of what these things look like, and away we go. So then often the volume scattering function or the phase function is more than what you need to know for your particular problem, or maybe you don't have an instrument to measure it anyway. So we have various integrals of that. The total scattering says take the volume scattering function at all angles and then integrate over all solid angle. And then that gives you the total amount of scattering without regard to what direction the light's being scattered. You don't care if more is going forward or right angles or what. It's just telling me the total amount. So remember, this guy is light that is scattered per unit solid angle, not just per unit scattering angle. So you integrate over all solid angles, and the element of solid angle, if it's azimuthally symmetric, is 2 pi sine psi d psi. So this thing here, this definition, is just how you get the scattering coefficient if you know the volume scattering function. And of course, you've now learned the scattering coefficient is beam attenuation minus absorption. Okay, so just keep in mind that this is telling you how much light is scattered without caring about what direction it goes into. Now, the idea is, look, we have this volume scattering function, and it both tells us the strength, how strong the light is being scattered, and it tells us the angular dependence. So it's got all of the information. The scattering coefficient basically tells us how much is being scattered. So that's kind of the strength of the thing. So you can say, look, let's take the total thing, strength and angular dependence, normalize it by the strength, and you'll get this thing called the phase function, which then gives you just the angular dependence without telling you how much light is actually being scattered. So that's the definition of the phase function. It's the VSF, volume scattering function, divided by the scattering coefficient. And so this shows you the shape of scattering. You know, is there more in this direction, more in that direction? But in the ocean, if you don't have very many particles, you won't have much scattering. If you have a lot of particles, you have a lot of scattering, but they'll both have the, both cases have the same phase function. So just think of this guy as being the angular pattern, this being the strength, and then the product gives you both the angular pattern and the strength of the scattering. Okay, then for remote sensing especially, the sunlight goes in the ocean, it's heading downward. If it's scattered in a forward direction, it just keeps heading downward and it's gone as far as you're concerned. So for remote sensing, you're interested in the light that's being scattered more or less back upward, because that's what's going to get out of the ocean and eventually make it to your satellite. So it's the backscatter coefficient rather than the total scattering that's of interest. And backscattering is just integrate from 90 degrees to 180 instead of 0 to 180. Same formula, just different limit on the integration. And that's how much is backscattered. And of course you can do 0 to pi over 2, and that's the forward scattering, and then the forward plus the backward is the total. So just another definition you've seen before. And there's something called the backscatter fraction then, which is the ratio of backscatter to total scatter, and that usually gets called either capital B or a little b with a tilde on it. So that's just the fraction of backscatter, fraction of the total scatter that is backscattered. And typically that's somewhere between 0.5% and 5%. Just depends on your particles. Okay, so that's just a definition to keep in mind. And there's one more thing that you'll see referred to, which is called the albedo of single scattering, and that's the ratio of scattering to absorption plus scattering. And so it's called the albedo of single scattering. It's a reflectance basically, it's non-dimensional, and it gives the fraction of light that is scattered when a photon interacts with a particle. The light can either be absorbed or it can be scattered. And so this is the fraction that is scattered as opposed to absorbed if there is an interaction. So it's called the probability of photon survival. So if there's no scattering, This is 0, all the light's absorbed. If there's no absorption, then this is 1, and all the light is scattered. So this just goes between 0 and 1, and it's just giving you a fraction of how much light is scattered whenever light interacts with the matter. And in the ocean, at most wavelengths like blue or green, this is typically like 0.85, 0.9, somewhere in there. But if you get out into the red wavelengths, absorption is very high, and this number is very small. Okay, enough said about that. So now the trick is to measure the volume scattering function. It ain't easy because you have to measure this full function of wavelengths, not just a single number. So there have been instruments developed going back decades. We'll look at some data from this fellow Ted Petzold. So he built some of the first instruments for measuring volume scattering functions way back in the late 60s, and there are even a few measurements before that. The problem is most of these instruments are unique. Somebody built them, they used them. Ken Voss has one called the GASM, General Angle Scattering Meter, that goes all the way back to the early days there. And so there's almost nothing in the way of a commercial instrument like an AC9 that you can just go buy and measure this thing. So therefore, the volume scattering function isn't measured very often, but it's very fundamental to understanding what's going on in the light field. And I'm not going to discuss these particular instruments. There has been sort of a new flurry of activity now of people developing instruments to measure the VSF because we really need to know it, and it's very variable, just like absorption. But anyway, I've listed a number of papers here by people who have recently developed instruments for measuring the VSF over, maybe 10 degrees to 170 and so on and so on. You can dig out these papers. There's a library there somewhere on the website, and I've put like 60 papers in there that anything I mention in my lectures, like all these references, those papers will be in there. There is now one commercial instrument. You're going to work with the list next week, a version that measures scattering from about 0 out to 20 degrees. There's now a version that goes something like 10 degrees to 170 that's called the list volume scattering function. And so that actually is a commercial product now that's just come out in the last year or so. So it hasn't gotten used much, but it does exist. Okay, so let's take a look at variability in volume scattering functions. So here's some of this data from Petzold going way back to the 60s. So the red line, it's labeled Turbid Harbor. That was actually measurements in San Diego Harbor. So who knows what kind of scuzz is in the water and mixed up sediments and whatever else. He's got one that's green called Coastal Ocean and one that's Clear Ocean, which was measured in the Bahamas. So if you just look at the volume scattering function for those water bodies, there's about 2 orders of magnitude difference as you go from very clear to coastal to turbid harbor water. If you just pick any one of these and go from, say, 1/10 of a degree out to 100 or 180 degrees, that's about 6 orders of magnitude in variation for any one of these guys. So when you're building an instrument, you need to have an instrument that can measure 6 orders of magnitude difference in the light field. Well, that's really hard to do. Your average camera off the shelf cannot come close to that. So often what you have to do is have one instrument that measures the very small angles, and it's adjusted for relatively bright light, and then you have a different instrument that works back here, and it's calibrated and adjusted for very small amounts of light. Then you have to piece those pieces together, and that all gets to be a real mess to do that. And Petzold's instrument that actually measured the angles up here was about 11 feet long, because he had to have this, just to design this thing. It's the way he had to do it. Anyway, here's the same thing now plotted on a log linear axis, and same story, just a different plot. And if you want to see, in this case, more of this stuff, if you want to download Petzl's data and play with it, often the pictures I'm showing you here are straight off of the web book. So, go there, look around under the scattering section, and there's a page on Petzl's data, for example. So anyway, just keep in mind, huge variability here depending on the water type, huge range, dynamic range, depending on the scattering angle. Okay, so here's an idea. Let's go back to the definition of the phase function, VSF divided by the scattering coefficient. Now you say, okay, look, I know these volume scattering functions are highly variable. They're going to depend strongly on the concentration of the particles by at least a couple of orders of magnitude. I know the scattering coefficient is highly variable, and once again depends on concentration of the particles. But maybe if I divide this highly variable function by this one, since both of these depend on particle concentration, maybe the ratio will not be very variable. And so I'll have just a function here that doesn't vary much with concentration, for example, and I don't have to deal with all the variability of the VSF. So the question now is that really a good idea? I mean, is it true or not? Well, we're going to get that by looking at some data and see. Okay, so Dr. Boss and company. Yes. Oh, sorry.
Can you go back to the slide? So, why is the graph going up?
Whoops. So here, or where it's back here, that's a typical characteristic of how particles scatter. For the physics of it, I don't know. Do you have a simple explanation of that, Ken? It's just the way things work. For your average oceanic particle or atmospheric particle, they tend to scatter the least somewhere around 120, 30, 40 degrees, and then they tend to go back up a little bit, sometimes by an order of magnitude. I don't know. I mean, it's some kind of complicated.
You think about Rayleigh scattering. Remember the picture there? It's absolutely symmetric. Most of the particles in the ocean are fairly low index. So even though they're larger, they have low index, and so they're sort of moving from a Rayleigh type particle, which is very small, toward the big particles by adding a bunch of scattering in the front. It still keeps some of the idea of the small particle. It's a Rayleigh Benz approximation, effectively, where you have a small particle and a low index combined.
So it's really that minimum around 90 degrees, which gets shifted a little bit when you start adding a lot of forward scattering. It actually shifts the minimum over to sometimes 110, 120.
Yeah. Does that work for a vague answer? And
There's a book by Jonas and Fournier that goes very deeply into it, and I have 3 plastic tubs full of books on optics. Anyone who wants to get deeper or understand that, they're in the lab under one of the desks.
And incidentally, I'm suffering the usual aches and pains of old age, one of which is loss of hearing frequency, or loss of hearing at high frequencies. So if you ask a question and I ignore you, just ask it louder in a lower frequency. Yeah, Kurt, hey, over here. And then I'll hear you. But if you're a woman with a very high-pitched, soft voice, even with hearing aids, I may miss it. But anyway, that works quite nicely with my wife, so I can always just ignore her. So, okay, anyway, yeah, to me, this is just a feature of oceanic particles depending on some complicated thing that's going on inside them. Okay, so then Emmanuel and Marlon Lewis and various other people took an instrument that was actually built by some Ukrainians, a guy named Michael Lee. They used this on a big Navy field experiment off the coast of New Jersey. So this instrument's measuring at 530 nanometers. The instrument's called the VSM, the volume scattering meter. And the Ukrainians will rent you this instrument if you want to rent it for a week and go to sea. So that's what Emmanuel and Marlin did. Okay, so here's 62 phase functions in green measured in coastal New Jersey water within a couple of days of each other and within a few kilometers of each other. So you would think, well, you know, this is probably about as close to being the same blob of water as you'll ever hope to see. It's not like one of these was in the Yellow Sea and one was in the Gulf of Mexico. This was just all off the coast of New Jersey. But even so, there's an order of magnitude variability in these spectra. So, and then here's, if you back up to Petzold's data, people will take these three curves, subtract out the water, normalize by the scattering coefficient and all of that, and then kind of take the average. And you'll see this, quote, averaged, Petzold averaged volume scattering function gets used like it was some kind of law of physics. So if it's not, but anyway, here's the average of the Petzold data after water's subtracted out. So you just have whatever's due to particles. And you see it runs right down the middle of the measurements. Well, that's cool. And if you happen to be in the water body that had this green curve, Petzold's going to be really close. But if you take the red curve, use it in Hydra Light or some other model, and you're trying to simulate this piece of water or this piece of water, you're off by like a factor of 2 or 3 or 5. And so you're going to get radically different predictions using Petzold if you're modeling this water or this water. Well, no secret there. It's just that people don't usually have the measurements, so they say, well, I don't know, I'll use Petzold. And then they can't figure out why they can't get closure between, you know, Hydra Light and whatever it was they measured. Well, yeah, you're off by a factor of 5 in your volume scattering function, so you're going to be off by a factor of 5 in your remote sensing reflectance comparisons or whatever else. So just keep in mind that something like Petzold or somebody else's function may be fine on average. It may give you a good typical value, but it may be really off in any particular instance. So when you start playing around with codes like Hydra Light, and you use things like Petzold, you're getting a perfectly good solution for average or typical conditions. But when you want to really compare Hydra Light's output with the data that you get on the ship out here next week, you really need to measure your particular curve, your particular absorption coefficient, your particular sky irradiance, etc., and run those through Hydra Light. But of course, you're not going to have an instrument to measure this next week. Okay, we'll get into more of that next week. Yeah.
So then, which angle would be the best to represent the whole curve?
Well, there are
Because that seems to be
the instruments that measure backscatter, which I guess you'll play with next week. There's a one called the HydraScat 6, and there's one called the BB9, and a couple of others. What they do is they really make a measurement at around 120 or 30 or 40, and then they put a fudge factor on that that kind of gives you an estimate of the value that if you knew this curve and integrated from 90 to 180, you'd get the scattering coefficient. But if you make a measurement here, there's the least variability in computing backscatter. But there's not really an angle that you could measure one angle and then get an idea of the whole curve, just because it's too variable. Does that answer? Yeah.
it's like constant. Like once you get one wavelength or one angle, then you can like get the whole.
Yeah, no, you know, it's just so variable. And of course, if we went to some other water body, Gulf of Mexico or Gulf of Maine or whatever, these curves would be still different. And so it's not really easy to pick some one angle and then say, I'll use that to scale some generic curve here. Just too hard to do. Yeah.
I may have missed this, but do the 62 green lines represent kind of water conditions that are very much similar to each other, or are they?
It's coastal New Jersey, so you sometimes in the coast, sometimes further out, sometimes closer to the bottom, sometimes closer to the surface, so there is.
Is that the experiment this moment?
That's radio. No, it's not. It was to mixing nothing. It was radio. So, I mean, and one of the 2 summers we were there. I mean, yeah, I mean, several days, coastal water is for, like some places there's more freshwater input, some places there's no suspension.
But it's not like the Pacific Gyre, clear water.
Yeah. There's a nice little saying that the ocean is inhomogeneous at all scales. So you go out there and you think, yeah, there's this blob of water here and it looks pretty homogeneous. But really, from here over to there, 100 meters away, there may be variability, almost always variability with depth. And this water was fairly shallow, so you get down deeper, you start getting resuspended sediments near the bottom, you get the phytoplankton near the top, you know, it's a mess. And you just have to recognize that that's the way the world works. So really what you need to do is for each station, you need to make a depth profile and get whichever curve it is at each depth. And of course you need to measure all the wavelengths, which is almost never done. This one's just at one wavelength. Okay, so as I've said, you know, when you're running Hydra Light or some other model, you might have measurements of absorption and scattering, say from an ACS, but you almost never have measurements of the volume scattering function. So then you have to guess what you're going to use, some one way or another. You come up with the wrong guess, then you can be way off on your Hydra Light predictions, and that's kind of just a common problem with running code where you don't really have all of the inputs. Okay, I just have to say a word about particle size distributions. You'll get a bunch more of this from a manual somewhere down the road, either tomorrow or next week. But this idea of a particle size distribution is basically a way to say how many particles of different sizes do I have in my water body or atmosphere or wherever. So there's what's called the number size distribution, little n of x. And that's how many particles there are per cubic meter per unit of particle size. And particle size, usually what you do is you take the volume of the particle and convert that to a radius. So when you've seen this plot here from Stramsky where it says particle concentration n of x per cubic meter per micrometer of size. And then here's this equivalent diameter here, so that's the measure of the size, and this is how many particles there are per chunk of size as you go across here, and you see this. And the straight line I've drawn through there, really the n of x is pretty close to x to the minus 4 power. There's then something called the cumulative distribution, capital N, and that's the number of particles per cubic meter that are less than size d in size or smaller than size d. So that's just the particle size distribution integrated from size 0 up to size d over the size range. And you'll see both of those. We're going to use this guy in our we have a Monte Carlo simulation or lecture in a couple of weeks. This is what we're going to live on there. There's what's called a Junge or hyperbolic size distribution that says the particle size distribution is proportional to x to the minus some power, where the power s is typically 3, 4, 5, somewhere in that range for the ocean. This curve, the s is equal to 4. And you'll also see people define area and volume distributions. So the list, for example, is looking at particles, and so it's the area of the particle that it sees that matters. So what people usually do is they say, well, let's assume the particles were spheres, and then I can convert a volume to an area or a radius. But of course, real particles are seldom spheres. Okay. The reason for showing you that is that scattering depends very strongly on the particle size distribution. And here's the proof of that. So Ensign John Gay here is probably no longer with us because he was flying at faster than the speed of sound, 25 meters off the sea surface. But what's happening, the plane's going supersonic. There's a shock wave coming off the nose of the plane and coming back like this, and there's another shock wave coming off the canopy. Okay, if you think of out here, think of a cubic meter of air. That has a certain amount of H2O molecules in it, but they're there as vapor. Now, they come along and they go through this shock wave, which greatly reduces the pressure. And then those air molecules condense out into being little water droplets, and you see this cloud. So it's the same amount of water, all you've changed is the size of the chunks of water, from being molecules to being little droplets that are, who knows, 1/10 of a micrometer or a micrometer in size, whatever, and boom, you've got a cloud. So very highly scattering, very low scattering. And then as the plane goes past, the pressure comes back to being the normal atmospheric pressure. The little water droplets all evaporate very quickly. You're back to water vapor and very low scattering. So just keep in mind that you think you're measuring absorption this week, and that's bad. It's really bad when you want to measure and compute scattering, because now you have to worry about size distribution, shape of particles, and internal structure. Just like you have pigment packaging with absorption, you have internal structure that does all kinds of horrible things to how the light bounces around inside particles. So anyway, just keep in mind that you have this size distribution effect that you're going to have to worry about. Okay, so let's just look at a few phase functions for water versus some other things. So here's the Petzold data here in red, and I've got some models we'll talk about. There's a thing called the Fournier-Ferrand phase function we'll see in about 10 minutes. So I've used it to compute the volume scattering function, the phase function for this N is the index of refraction, the 4 and the 3.5 here, that's the slope of the Junge distribution. And so I've got three things there. So I just computed, here's what these various ocean particles look like. So you can think of the purple as kind of low index of refraction, typical of phytoplankton. The 1.1, the 1.2, those are more typical of high index of refraction mineral particles, but they all have rather similar phase functions, rather similar if you realize this is a log plot, so there's like a factor of 5 there. And if you haven't learned it, it's very important for graduate students to know that if you want to bury the variability plotted on a log scale, and then that looks really close, but oh really that's a factor of 3 or 5 or 10 or whatever. So you can hide your errors, and if you're really good, you can slip that past the committee in your final dissertation defense. Okay, so here's one now where the fellow measured the VSF of microbubbles. So micro meaning these really little guys like 10, 20, 30 nanometers in size. So he says the bubble distribution followed a log normal distribution with a mean of 25 micrometers, so on down the line. And he's got measurements here, says produced in clean seawater, solid line, and surfactant contaminated seawater, dotted line, compared with the theoretical phase function calculated for clean bubbles, which is the dashed line. Now, the theoretical calculation was me theory. You're going to be doing some of that next week. And this is one of the few cases where me theory is perfectly good, because you have spherical, homogeneous air bubbles. You're good to go. But notice here, the red is the Petzold curve from over here. Here there's, a lot less scattering by the bubbles. Here it's sort of 60, 70 degrees. There's an order of magnitude more scattering by the air bubbles. This is 2 orders of magnitude here, and so that's about an order of magnitude. Then there's less for a while, and then the bubble scattering goes way back up by an order of magnitude as you get close to, past 160 degrees, but in the back scattering. So it's a good bit different than the typical particles we have in the ocean. So if you want to include bubbles in your Hydra Light simulation, which you can do, you need to go out and get one of these phase functions and be sure to use that guy for the bubbles. Don't use Petzold for the bubble phase function, because you didn't really measure the bubble phase function. Just be forewarned. There's folks in Poland, Otręba, Piscosub, several others have done a lot of simulations of the effect of oil droplets in water, because they're interested in doing things like remote sensing detection of oil spills. And when you have an oil spill, usually the oil breaks up into really small little droplets, and you get this sometimes they call it chocolate mousse, but it's basically a suspension of really small oil droplets. So then if I have water with a lot of these little oil droplets, what do they do to the light field? Well, they've computed here once again, and some measurements also, the VSF, phase function in this case, of these oil droplets. Notice he's got here, he says clear ocean and turbid harbor, the kind of line that keeps going straight up. That's Petzold's data for comparison. And then they've got the phase functions for the oil droplets that are a day old, a week, 2 weeks, 5 weeks. Well, when you first have the oil spill, you have lots of little droplets in the water. As time goes on, they sit there and they age, and sometimes they, coalesce, and you get bigger droplets. And instead of being kind of a clean, fresh oil, it's sort of the volatiles evaporate off, and you end up with these little kind of almost tar balls sometimes. So the phase function is changing shape here as time goes on. And here he's also now shown, I think these are all the 750 nanometer curves here. It also depends on wavelength. Well, here there's almost an order of magnitude dependence at the small angles. There's much less out here. And notice there's also a very weird little bump here that you see at sort of 90 degrees or 80 degrees, somewhere like that. You don't see that kind of bump in the Petzold data, for example. But there's something going on in the oil droplets that gives you a significant amount of scattering, more, at least a factor of 5, at around 90 degrees. And so you want to see what oil droplets do to the light field. You need to account for that. Here's water droplets in air instead of air droplets in water. And you see here the droplets, there's a really steep section of the curve here. That's due to diffraction around the water droplets. And now there's a couple of bumps out here that you don't see in the Petzold phase function. Well, those bumps, there's one here, that's what gives you the rainbow. There's another little bump out here near 180 or 170. That's what gives you a thing called the glory. So if you draw a line from the sun through your head, then the center of the rainbow will be on that line, or the center of the glory will be on that line. So there's a whole lot of atmospheric phenomena that you get from little bumps in the phase function, or if you wish, the little phase function is representing things that go on inside water droplets in air, about how there's internal reflections, and I'm sure you've all seen these kind of diagrams to explain how light gets in, it's refracted, it's reflected off the inside of a droplet, it eventually gets out, and you get the rainbow. And of course, since from the sunlight through the photographer's head to the center of the curve, which is about right here, so you can tell this guy is probably flying in first class. He's not in the back of the plane back here. So you can get a lot of information out of something like that. And you can see there's additional rings here that sometimes you'll see 4 or 5 of these rings because the different colors. That's, if you notice, the wavelength shift from 440 to 555 and so on. So the angles at which the scattering is strongest depends on the wavelength, and you get these really cool colored phenomena. Okay, here's this one more atmospheric one. For ice crystals, things get really complicated because they're not little spherical particles. They have real structure and all kinds of hexagons and plates and snowflakes and little pyramidal shaped things. And they're usually big compared to the wavelength of light. So light can come through these ice crystals in various ways. If it comes through here, it tends to come out at about 22 degrees. If it comes in here and goes out the end of a hexagonal plate, that's sort of 46 degrees. And the solid line here is the phase function for ice crystals like this. And you see there's a bump here at about 22 degrees. There's another one at about 46 degrees. And that's what gives you a lot of these ring around the sun effects, or halos. So here you're seeing a ring here. That's the 22 degree peak. There's a bigger ring out here. That's the 46 degree peak. There's the sun. There's a couple of spots here which are on the 22 degree ring. Those are called sundogs. And a lot of times you'll only see the sun and these 2 spots here. If the crystals are oriented all kind of the same, you'll only get one part of the ring. If the crystals are randomly oriented, then you'll see the whole ring. And here's something else up here, not described in this thing, but some other shape of ice crystal giving some weird bump in the phase function, and it's not the same for all azimuthal angles, it's only certain angles. So those of you who are lucky to live in a nice place like Alaska or Canada, in the winter you'll see these kind of phenomena, fairly often. The ring around the sun, which you can see almost anywhere, you're looking through ice crystals in cirrus clouds, and you'll get this ring around the sun. Now and then you may see the second one, but in the northern latitudes or in a place like Antarctica, you get just some incredible displays of all kinds of rings and arcs and colors. And there's notice here, you can barely see, there's what's called a circumhorizontal thing that'll go all the way around you, all the way around the horizon. So a lot of strange stuff, and it's all due to different shapes of ice crystals in either randomly oriented, or if they're not randomly oriented, if the air is cool, then let's say we have little plates, they'll all settle down like this. They won't be randomly oriented. So that'll give you spots at various locations, here, here, and so on. And there's a book called Rainbows, Halos, and Glories by Robert Greenler that's got like 100 of these different pictures. And then he's done Monte Carlo ray tracing to figure out what shape and what orientation of ice crystals do you need to reproduce all of these different things. So it's a fun little book.
You can make a lot of those yourself. I made a little triangular, take 3 glass slides, glue them together in a triangular form, and add end caps and fill it with water. And then put that on the end of a drill. And if you spin the drill, you let this drill spin, put it in the projector,
Yeah. Yeah, cool. Okay, I hadn't thought of that. See, you can tell Ken's an experimentalist, and I'm a theoretician. I do the Monte Carlo. He gets the thing out and puts it on a drill. Okay. All right, enough said for this kind of stuff. Just keep in mind that what the VSF is really doing is parameterizing all of these complicated things of internal reflections and surface reflections and, diffraction around the particles. It's taking care of non-spherical particles. All of that ends up just giving you this little curve that you can work with. So you don't have to understand why the curve is like it is if all you want to do is compute what light does in the ocean. You just take the curve, you're good to go. Okay. Keep in mind that the magnitude of the VSF depends on concentration of the particles and, of course, also on wavelength. That's the scattering coefficient. The shape of the VSF, or the phase function, that's determined by particle size, particle shape, internal structure, and also the index of refraction, and that depends on wavelength, so does the VSF, although maybe a little less than the whole scattering coefficient does. Keep in mind that everything you looked at here is for unpolarized light being scattered into unpolarized light. If you're dealing with polarization, which you always have if you're shining a laser in the ocean, then you'll have a VSF that says, well, if I have polarization in this direction and it scatters into this direction, there's a VSF for that. If it's linearly polarized and it scatters into circular, what's the VSF for that? If it's unpolarized and it scatters into this linear polarization, there's a VSF for that. So you end up with 16 of these things because there's these 4 Stokes vectors or Stokes parameters that Ken will talk about, and you can go between any 2 of those. So you really have a 4x4 matrix of volume scattering functions in general. And then everything I showed you here is for isotropic media. That means the optical properties are the same no matter what direction I look, and that it's for randomly oriented particles. If the particles are not randomly oriented or the properties not isotropic, let's say you were inside a quartz crystal or a calcite crystal, light will propagate differently in one direction than the other, then all of this stuff has azimuthal dependence as well. Okay, so now let's take a look at how you model some of these things so you can use it in a... Yes?
So if you're using Hydra Light in really turbid waters with lots of sediment, does it matter it would matter what type of sediment?
Yeah. And, at that question, you're kind of pushing the frontiers of optical oceanography. When you run Hydra Light, I have 4 or 5 typical kinds of mineral particles in there, and you can pick one or the other. And they're significantly different. But there's really very little data on this. So you're at the point where you need to measure whatever particles you had in your water. You can't just assume that it was one of the ones that's in the Hydra Light database. And you can assume it and you may luck out, but it probably will be different. Okay, so we'll talk about modeling, scattering by water, by phytoplankton, by CDOM, which is the easy one, non-algal particles, and then there's organic and inorganic and so on. And then we'll take all those pieces, stick them together, and next week you'll see these IOP models that are based upon these different pieces. Okay, so as Colin has said, and I'll say it again, IOPs are additive. So the total volume scattering function, if you have indifferent components in your water, which will be water, this phytoplankton, that phytoplankton, this mineral particle, bubbles, CDOM, whatever, you can study each one of those guys individually, get their volume scattering functions, and then add them up and get the total. Now, remember, beta, the VSF, is the phase function times the total scattering. So if I write this as beta tilde times total scattering coefficient, I can get the total phase function, and then over here, divide through by B, I'll have that the scattering coefficient for each component divided by the total scattering becomes a weight for the phase function for each component. So usually what you do is you have phase functions for different kinds of components, this mineral, this phytoplankton, that phytoplankton, and you say, okay, that's determined by the type of particle. Then how important that contribution is depends on how much scattering it's causing relative to the total scattering. So just keep in mind, VSFs are additive, phase functions are additive, but they have to be weighted by the relative amount of their contribution to the total scattering. And then when we write an equation like this, well, what makes sense for what components to add up? You'll always have water, then you can have phytoplankton, different kinds of mineral particles, bubbles, oil droplets, whatever's in the water. And that's your choice. So, okay, so if we look at scattering by pure seawater, there's what's called Rayleigh scattering, which is for spherical particles, and that's the green curve here. Here's its phase function. Notice it's symmetric about 90 degrees. Equal amounts of forward scatter and back scatter. Now, if you actually measure the phase function for water, it's not quite the same as Rayleigh, and that's because water molecules are not spherical. So they're a little bit of difference, but not much. And in Rayleigh's original work, when he was assuming spherical homogeneous particles, he got the green curve there. And then if we look at how does the total scattering depend on wavelength, Rayleigh came up that it's proportional to wavelength to the -4. For water, it's really wavelength to the minus about 4.32. And that's once again because water molecules aren't really spherical. So the scattering spectrum for pure water is a curve like this that basically depends on lambda to the -4.3 roughly. And then there's a phase function that is really not, the green curve is a 1 plus cosine squared. The water one is really 1 plus 0.8 cosine squared. So a little bit different. So some people will say water is Rayleigh-like scattering. It's not really Rayleigh scattering, which would be the green curve. And you can screw these pieces together, the phase function, the scattering coefficient, and you get a water volume scattering function, which you'll see as the wavelength and scattering angle dependence is usually the value for a reference wavelength at 90 degrees. Then the other wavelengths come from the lambda over reference wavelength to the -4, and then the phase function part is 1 plus the cosine squared term. Well, then where do you get this thing here? Well, you go to the literature and there's a bunch of tables where people have measured things like the volume scattering function at 90 degrees as a function of wavelength, and there's the total scattering for this is pure seawater and pure water. So all of this kind of stuff is built in to the databases that are down inside Hydra Light, so it knows what to do for pure water. It's the only thing it knows. Notice if you take the value for pure seawater, so here's a percent bigger. So pure seawater and pure water have basically the same